Okay, hello and welcome to my channel. Today we're gonna be talking about the step potential, and this time we will include the scattering state. So we're gonna take a look at three cases. So the first one is that our E is greater than our potential V naught. Second one is our E would be equal to our V naught. And the third one is that when our E is less than V naught. And today we're just gonna be talking about the scattering state, which is the first one when E is greater than your V. Alright, so let's start. So we will consider our E to be greater than V naught. And step potential, meaning that your potential take a step up. So here to x equals 0, it's gonna take a step and jump up to a V naught, meaning that your potential V of x is 0. Okay, your potential V of x is equal to 0 when your x is less than 0, and when your x is greater than 0, it is equal to V naught. Right? And your energy, as I said, would be greater than your V naught. It's gonna sit there, called scattering state. Right? So what we want to do here is figure out how our wave function would look like in this region and this region, since the potential here is not infinite, so there would be some of the wave function that managed to leak through, and that is called quantum tunneling. Okay, so when you send in a wave function, it's gonna reach this point x equals 0, and from here, as I said, if classically, it would bounce back. But this is the quantum world, so there would be some that leak through, and that is called quantum tunneling. Okay, so this region we will call the initial wave function that we sent in is a exponential ikx. So this region we would use k, and this region we would use k tilde. So that would indicate that here would be different from here, our two wave function. So the bounce back, the one that bounced back, we will say that it is equal to a b times e to the minus ikx. Okay, next is here, the one that got through, we would call it c to the e I k tilde x. So to sum it up, I'm gonna write our wave function to be ae to the ikx plus b to the be to the minus ikx when x is less than 0, and c e to the ik tilde x when x is greater than 0. So this would be our wave function in the two region with the energy equal to h bar squared k squared over 2m. This would be our state. K here is 2m h bar e, and our k tilde is 2m h bar. Here e is greater, so e minus v naught. Right? It's h of square. Sorry. Alright. Next, we would take a look at the condition for this to be satisfied. So we got our point x equals 0 here. So we would have to demand that it is continuous at psi 0. So for it to be continuous, so psi is continuous at x equals 0. That would mean that your wave function and its derivative have to be equal to each other in the two regions. So it's gonna be a plus b equal to c, and IKA plus minus IKB equal to IK tilde C, which you can rearrange that and say that A minus B equal to, okay, so you can say that I minus B is equal to K tilde over KC. All right, so now you have this, you can get now the coefficients, the transmission and the reflection coefficient. So the rate that would get bounced back and the rate that it would get through here. And to do that, we take B over A, calculate that, and it would be K minus K tilde over K plus K tilde. And our C over A is 2K tilde over K plus K tilde. Oh, it's 2K, right? And these two are called the reflection coefficient, and the transmission coefficient. All right, and that is all you have to know about the scattering state of the step potential. So that would be it for today. Goodbye.